Hi, welcome to Algebra 2 Common Core. In today's lesson, we're going to continue looking at the discriminant and how this predicts the number and nature of the roots that a quadratic is going to have. So first of all, let's recall what our formula is for the discriminant. Remember in the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. The discriminant is just the part that's underneath the radical. So therefore our discriminant is going to be b squared minus 4 times a times c. So let's look at the first equation. Y equals 2x squared plus 3x minus 2. In this quadratic equation, we see that a is equal to 2, b is equal to 3, and c is equal to negative 2. So let's calculate the b squared minus 4ac. So we'll have 3 squared minus 4 times 2 times negative 2. And putting that on our calculator, we see that that answer turns out to be 25. So our discriminant value is 25. Notice that this is a number, a discriminant, that is a positive number, and it's also a perfect square. So from that discriminant, I can then go ahead and solve for my roots. So let's put that in the box below. So I will have x is equal to the negative of b, so negative 3, plus or minus the square root of that discriminant, so the square root of 25, all over 2 times 2, which is 4. Now, because I've got a perfect square, I'm getting x is equal to negative 3 plus or minus 5 over 4. This gives me two roots. Negative 3 plus 5 is 2 over 4, which reduces to 1/2. And negative 3 minus 5 is negative 8 over 4, which reduces to negative 2. So I can describe these roots by saying that they are real. Notice that they don't have an imaginary part of them. They are rational because they could both be written as fractions. And they are unequal because I have two different roots. So the number of unique solutions, there are two unique solutions that are both real solutions. Now, if you'd like to, you can take out your graphing calculator to help you graph this parabola. I'm going to make a table of values. Using my calculator, I see some of the important points on here. Negative 2, 0. Negative 1, negative 4. 0, negative 2. And 1, 3. So when I graph this, I of course am crossing the x-axis at both negative 2 and at positive 1/2. And I see that I'm coming and crossing the y-axis at negative 2. And I can make my parabola. Sketching it out, it looks something like this. So clearly on this graph, I see that I am crossing the x-axis twice. That tells me I have two real roots. So all of this information all fits together. Whether I look at the graph and see that my graph is crossing twice, or whether I look at the discriminant and see that the discriminant is a positive perfect square, or when I solve for the roots, I also see that the two answers are unequal, but they're real and rational. So all of this information fits together. This is going to be scenario number 1. So when I have a positive perfect square discriminant, all of these pieces have to fit together. Let's go ahead to scenario number 2. So our second example, y equals 9x squared minus 6x plus 1, I'm again going to start with my discriminant, so the b squared minus 4 times a times c. The b is negative 6, so negative 6 squared minus 4 times 9 times 1. And when I do this, I see 36 minus 36 giving me an answer of 0. So in this case, I see that my discriminant is equal to 0. That's going to be significant for us when we're describing the nature of the roots. Let's find the roots first of all, and I'm going to continue on with my quadratic formula. So I'm going to say x is equal to the negative of b, so negative of negative 6 is positive 6, plus or minus the square root of 0, all over 2 times 9, which is 18. Now in this case, I am getting two solutions, 6 plus 0 divided by 18, and also 6 minus 0 divided by 18. But if I'm observant about this, I see that actually they're exactly the same root, x equals 1/3. So when I have a discriminant that is equal to 0, I can describe my roots as real, because again, I do not have an I in my answer. Rational, because I can write those roots or that only root as a fraction. But the two roots are equal to each other. Both of them equal 1/3. So in this case, what I have is one real solution. So when the discriminant is equal to 0, that's always going to go with one real solution. Now let's go ahead and graph this. I see that my root has to be 1/3, so I'm going to put the dot at 1/3. And when I graph this, my y-intercept is 1, so I'm getting a graph that looks something like this. And I see that my graph touches the x-axis only once. And the one place it touches is my root 1/3. There's a name for that when I touch the x-axis once. It is called tangent to the x-axis. Tangent means touches in one spot. So again, all of these pieces go together. When the discriminant is 0, the graph is going to touch the x-axis only once. I get one solution, and that one solution is always going to be real and rational. Now let's go to example number 3, y equals 3x squared plus x minus 1. Solve for the discriminant, b squared minus 4ac. So in this case, I am getting the b is equal to 1, so 1 squared minus 4 times 3 times negative 1. And that's giving me an answer of 13. Now 13, while it is positive, is not a perfect square. So let's go ahead and solve for the roots using the quadratic formula. X is equal to the negative of b, so negative 1, plus or minus the square root of b squared minus 4ac, well that's just the discriminant, all over 2 times a, so that's all over 6. So I again get two solutions. My first solution, negative 1 plus radical 13 over 6. And my second solution, negative 1 minus radical 13 over 6. So these answers, if I were to put those in my calculator the way that I did the last couple units, I could round these or simplify them just approximately equal to 0.4, and x is approximately equal to negative 0.5. So that'll help me graph. So if I look at my graph, I see that I'm again crossing the x-axis twice, and I'm going to cross at approximately negative 0.5 and positive 0.4. So crosses the x-axis twice. Now let's describe those roots. I see that my roots are real because they don't have an imaginary in them, no I. But this time, because I don't have a perfect square under my radical, I have irrational roots. So because the square root of 13 stayed in there. And I got two roots, so they are unequal to each other. The two places where the graph crossed the x-axis were two different spots. So my unique solutions, I have two real solutions. So this scenario is just slightly different than the first example that we had, because in the first example, my discriminant was a perfect square. So therefore my answer was rational. In this case, the discriminant was not a perfect square, so my roots are going to both be irrational. Now let's see what we're going to have for our fourth example. Y equals 2x squared plus 3x plus 4. So let's solve for the discriminant b squared minus 4ac. And again, remember, we look at the discriminant when we are trying to describe our roots. So b squared minus 4ac, I've got 3 squared minus 4 times 2 times 4. So that's giving me negative 23. So this is the first time that my discriminant has been a negative discriminant. And I think you can probably guess what's going to happen when that discriminant is negative. Let's go to our quadratic formula and solve for the roots. So x is equal to the negative of b, negative 3, plus or minus the square root of negative 23, all over 2 times a, so that's all over 4. Now, because I've got a negative number underneath my radical, I'm getting negative 3 plus or minus I radical 23 all over 4. So I have two solutions, but these two solutions are both imaginary. So I have imaginary roots. Whenever they're imaginary roots, those roots are going to be called complex conjugates. The real parts match, the imaginary parts are opposite of each other. So the number of solutions, I actually have two non-real solutions. And again, non-real means they've got an imaginary in them. There's an I in my answer. Now, take a look at your graph of this. Take a minute to enter the equation into your graphing calculator and make a table of values, and then go ahead and plot the points and come back and see if it matches with mine. Notice the difference. When I graphed this parabola, this was the only situation when my graph does not cross the x-axis. So if I graph a parabola and I see that the graph never crosses the x-axis, automatically that's going to tell me that I'm going to have two non-real solutions. And my solutions are going to be complex conjugates of each other. I can also predict that the discriminant would have had to have been a negative answer. If I solve for a discriminant and I get a negative answer, then that's going to tell me these other two things. My roots are complex conjugates, and my graph will not cross the x-axis. So all three of the pieces have to go together. So we've been doing some work with the nature of the roots today. Tomorrow in class we'll continue looking at the discriminant as well as the graphs and the types of roots that we have. Thanks very much. Have a great night, and we'll see you next time.